Good morning to one and all present here. Hope you all are safe and sound. On behalf of ISI Bangalore students, I welcome all participants to the 7th and last day of the Mathematics Online Camp of Training. I have great pleasure in welcoming Professor Sucharit Sarkar to this platform. Professor Sarkar obtained his BMath degree from ISI in 2005 and was awarded his PhD in mathematics by Princeton University in 2009. He has been awarded gold and silver medals in the International Mathematical Olympiads and has also been a recipient of the Clay Research Fellowship. Professor Sarkar is currently an associate professor at UCLA, where he was awarded the Sorgenfrey Distinguished Teaching Award. He is also an editor for the journal Selecta Mathematica and a board member of Pacific Journal of Mathematics. His research interests include low-dimensional topology, symplectic geometry, and algebraic topology, with particular interest in knot theory. With great honor, I welcome the professor to enlighten us on the Borsuk-Ulam Theorem. Before we begin, I request all participants to keep their mics muted, unless any questions, in which case they may unmute themselves and ask or type in the chat. So,
Okay, should I? I'll just wait for 3 minutes because, but it's still shared, right? So, I'll just wait for 3 minutes and then we'll see. Yeah, and if you, so I cannot see your faces, right? Because it's like I'm sharing the screen, just letting you know. So I won't be able to see facial reactions or anything. So if you have questions, just unmute yourself and interrupt me, okay? And that's fine. So, but I won't be able to like look for reactions. And oh, I'm at the thing. I will be. My stylus stopped working, so I'll be writing on this computer itself with my fingers. So, you know, the handwriting will be slightly illegible, but yeah, it's but that's okay. Hopefully you'll be able to understand it. Yeah, it's not going to be a blackboard talk, right? So I'll be just writing on the computer. So, but again, if you cannot read it, just let me know. I'll try to write it larger. Okay, so I'll turn my video on. Can you see me?
Yes, sir.
Okay, great. So, chalo, let's see. Yeah, so let me start. Okay, so by the way, is this camp is it happening in ISI or is it like virtual?
No, sir, virtual.
It's virtual. Okay, so it's all of you are like in all parts of India, right? Okay.
Yes.
Stay safe wherever you are. You know, get vaccines if you can. But yeah. So okay. With that being said, yeah. So. But usually every year it's at ISI. Is that how it works?
So we are organizing this for 3 years, and for first year there was no COVID, so we could organize in ISI only. But the last 2 years we are doing online.
Okay, but no, this is good. This is good. Like yeah, that's great. Yeah. And I mean we didn't have this, right? Or we didn't like so. This is yeah. It'll be good. I mean hopefully by next year it'll again be back on at ISI. So that's great. Okay. So you did it at the auditorium or something, right? Like 3rd floor.
I don't know because I am a first year now, so.
Oh, so you have no idea. Okay, I see. Okay. Oh, so you have maybe never been to ISI, right? Or
So, sir, for one time only, just for admission.
That's I see. Okay, so okay, they have an auditorium which is pretty large. Okay, so okay, chalo, let's start. Okay, so I'll talk about this theorem called Borsuk-Ulam Theorem, but the way I studied it in abstract, it's a very famous theorem in topology, and it is not an obvious theorem. Okay, so the way I studied it in the abstract is like at any instant of time, there are two antipodal points. Antipodal means like opposite points on Earth, on the surface of Earth, which have the same temperature and pressure. It's like a pretty stunning statement. Okay, and it's not obvious to prove. It's a mathematical statement. It's not obvious to prove. and it really uses like topological techniques. Now I understand that at the camp there is like a big range of students, like from like high school students and like, you know, class 8 to like, you know, first year college students. There is a big range. So of course, any talk I give is not going to be like, not every bit will be good, will be perfect for everybody. It's like a big range, but hopefully everybody gets something out of it. Okay, so there'll be like some elementary bits which hopefully like the, you know, the class 8 students will understand, and then there'll be some technical bits which will be like appealing to the college students. Okay, so some part might be fast for somebody, some part might be slow for somebody, but hopefully on the whole everybody gets something out of it. Okay, and that's fine. You don't have to like understand the whole part, but let's see how it goes. Okay, but feel free to interrupt for questions and everything. Okay, so the abstract statements I will write very little because I have to like write on the, it's not like writing on the blackboard, so I'll try to just write on the screen with my fingers. So it's harder. So I'll just mostly say things. Okay, so here's a statement, right? So at any point of time, there are two antipodal points on Earth, on the surface of Earth, which have same temperature and pressure. It's not a geography statement, it's a math statement. And the way you like kind of say this in math is as follows, that let's say, so I'm talking about the sphere, of course. So there is S2. S2 is like the unit sphere, is the set of all points x1, x2, x3. In R3, yeah, so my handwriting is not ideal. I'll write it larger so that, you know, it's unit distance x1 plus x2 square plus x3 square is 1. Okay, so that's the sphere, and let's say I have a function. Okay, I'll write it larger. I have a function from S2 to R2 which is continuous. I have a continuous function. So just think of it. So S2 is like the surface of the Earth. And I have a two variable function on the surface of the Earth. Okay, so a function from S2 to R2, which is continuous. So just like the temperature and pressure. So I have a two variable function on the surface of Earth, which is continuous. And the statement is the following. The statement is saying that at any point of time, like, so there are some points. So there is like, there exists some pair of antipodal points, x minus x on the surface on S2. So there are two antipodal points, x and minus x are antipodal, such that f of x is equal to f of minus x. So given any continuous function, there are some antipodal points where the value of the function must be equal. Okay, so that's Borsuk-Ulam theorem. Yeah, not obvious at all, but let's see. So if, even before, okay, so you understand, like this is the statement that at any point of time, there are some antipodal points on Earth which have same temperature and pressure. Okay, so before we start this, let's do so this is actually true in all dimensions. So this is the case which is dimension 2. But Borsuk-Ulam theorem is actually true in all dimensions. So instead of doing dimension 3 and dimension 4, let's do the lower dimension. So let's do the case for dimension 1. Okay, so the dimension 1 is as follows. So instead of the sphere, I have the circle. So I'll write the circle also. The circle is like all the points x1, x2 in R2, so that which is unit distance, x1 square plus x2 square is 1. Okay, so that's the circle, and it's saying that if I have a function f from the circle to R, if I have a single variable function on the circle, so then there exists a pair of, it's exactly the same, which is continuous. All my functions are continuous. Then there exists a pair of antipodal points on the circle, so that it's exactly the same statement where the function takes the same value. So it basically says that if I have a continuous function on the circle, then a real valued function, then some pair of antipodal points on the circle must have the same value. Okay, so I don't know if you have seen this statement. If you have seen the statement and you have seen the proof, you know, you'll realize that the proof is actually very beautiful. There is a nice trick, and the trick is beautiful, and you know, it's really fun. I'll show you. If you haven't seen the proof, you can try doing this, but it is quite tricky. Okay, so you know, there is a trick involved, and it's hard to figure it out. I mean, once you see the trick, it's very easy, but until you see the trick, it's hard to do it. Okay, but if you haven't seen the trick and you have still figured it out, I mean, that's great. Okay, that's very impressive. But so here is the trick. Okay, but this actually, since I'm not seeing you face to face, it's hard to like ask for it. But so I'll just tell you what the trick is. And here is the trick. The trick is you define a new function, which is like g of x is the value of f of x minus the value at its antipode. I mean, this is also a continuous function. So you just take the value of the function minus the value at its antipode. So you just define it like this. So this is actually a new function that you just define like this. Okay, I'll highlight this. Yeah, that's the trick. And then this G actually has a nice property, namely the G actually is what we call odd. So G is an odd function. Sorry, G is odd. Namely, G, just from the definition, it satisfies that G of minus X is minus G of X. I mean, G is also a function. G is also a function from the circle to R, but it's also a continuous function. But if you take the value at its, like if you negate the input, you're also negating the output. I mean, it satisfies this. This is obvious from the definition. So G is an odd function. So G is an odd function from the circle to R. And what do I want to show? I want to show that G is somewhere 0, because I want to show that f of X is equal to f of minus X somewhere. I want to show that that holds. So that means I want to show that G of X. So I want to show this, that there exists X such that G of X is 0. So if I have an odd function from the circle to R, it must be 0 somewhere. Okay, so and that actually is the trick. And then how do I prove that? That actually turns out to be much easier. So here is how you prove it. Let me draw the circle. So here is the circle. And let's take any point, doesn't matter. Let's take this point, X. Well, what is the value of G at that point? Well, there are really 3 options. I mean, G could be 0. If G is 0 there, I'm done, because I just want to find a place where G is 0. If G is 0 there, I'm done. Tick. Or G could be bigger there, positive there, or G could be negative there. Those are the only 3 options at that point. If G is 0, I'm done. Well, if G is positive or G is negative there, we'll look at the value at minus X. So minus X is its antipode. Well, remember, when you negate the input, you negate the output. So if G is 0, well, G is still 0 here. But if G is positive, G must be negative here. And similarly, if G is positive at X, G must be, if G is negative at X, G must be positive at minus X, right? So for these 3 options, those are the corresponding options for minus X. And now you notice that there is this sort of thing that I can now just walk from X to minus X. Let me just walk from X to minus X. And because G is a continuous function, if G was positive here, it eventually becomes negative. So by intermediate value theorem, somewhere in between it must be 0. Similarly, if G was negative here, it eventually becomes positive. So somewhere in between it must be 0. So there is like some intermediate, this is like the intermediate value theorem. G is continuous, it's intermediate value theorem, it's positive here, negative here. So somewhere in between it must be 0. So that's it, that's a proof. It's a nice trick, but that's the trick, that's a proof. Any questions? No? Okay, let's move on. It's a very beautiful trick. If you haven't seen this before, it's very nice actually. So. Okay, so now, but this is a one-dimensional case. So by the way, the one-dimensional case again is like the way people write this, and I'll just say this, like the way you would most probably say this is at any, and this is actually also hard. You can tell this to your friends, right? I mean, at any point of time, there are 2 antipodal points on the equator which have the same temperature, because a circle is like the Earth's equator. Circle is like the Earth's equator, and you can say that at any point of time, there are 2 antipodal points on Earth's equator which have the same temperature. It's only one variable, so you can only say temperature. Okay, so but that's also a stunning fact actually, and not obvious at all unless you know this trick. Okay, but now let's go back to, but there is no topology here. This is just intermediate value theorem. But now we'll go to topology. I do topology. I'm a topologist. So let's go back to like the original statement that we were doing. So the original statement we were doing is like, so I have a function like this. And I'm trying to show it's a 2 variable function on the whole sphere on S2. And I want to show that there are antipodal points which are the same value. OK, we start using the exact same trick. So namely, I mean, let me just repeat this. OK, so now we're back to dimension 2. Back to dimension 2. You do exactly the same thing. You still define G of X to be f of X minus f of minus X. It is still a continuous function, but except G is now a function from S2 to R2, which is continuous and odd. Namely, if I negate the input, I negate the output. Okay, so G is still an odd function. It's a continuous function, but it's now a two variable function on S2. And I still want the same thing. I want to show that G is somewhere 0. So we want, like, what we want is that there exists X. There exists X so that G of X is 0. This is what we want. And so how would I get this? So you do this by contradiction. So you prove by contradiction. So you assume not. So I'm going to give only a sketch of a proof because the proof is actually hard. It's not obvious at all, and you need a lot of like college level math, like even beyond that, like even beyond, you need mathematics beyond what you will learn in, like, for instance, ISI BMath program. I mean, there is math involved here, which is like more than that. So I'm going to just like give a sketch of a proof because there is no way I can describe the whole proof. So I'll give a sketch of a proof, but hopefully you get something out of it. Okay, so the proof is by contradiction. So you assume not. So you assume otherwise. Yeah, this is my finger handwriting, but so you assume otherwise. So that means you assume that there is some odd function G which is nowhere 0. Like, so G of X is not 0 for all X. Okay, so you just assume that. So now what I can do is I can define a new function which we call h of x to be g of x divided by its length. Okay, because the length of g of x is not 0. So g of x is like a two variable function. It's a vector. It's a two-dimensional vector. So I can divide by its length. The length is not 0, so I can divide by its length. So now h is like, let me just write this. H is a function from S2 to S1 from the sphere to the circle, which is also odd. So it's a continuous function and it's also odd. Namely, if I negate the input, I negate the output. Okay, so it's an odd function. So I have a continuous odd function from a circle S2 to S1, and I just have to show that this is impossible. Okay, I'll get a contradiction. So I will show that this is impossible. Okay, why do I get that this is impossible? Now, okay, so now we are getting to the heart of it. Any question up to here? No? Let's see. So here is a picture, and this whole proof is really contained in this picture. So here is R, here is S2, here is S1. So I have this function, this odd function from S2 to S1. Okay, but there is also a function from R to S1, and I'll tell you what that function is. So this function, let's give it a name. I'll call it pi. Maybe pi is a bad name. Let's call it P. I wanted to say P for projection, but let's call it P. Okay, so there is a function called P, and the way P is defined is P of T is like e to the 2 pi I t. Okay, so if t is a real number, 2 pi I t is a complex number, but it's a complex number which is length 1. It's a unit complex number. There is, like, maybe if you're a high school student, you don't know this yet, but it's a unit complex number. So it's a point in the circle. Okay, so it's a complex number of length 1. So you define this. So if it's a real number, you just send that to e to the 2 pi I t. Okay, so it's a function like that. Now this function is actually sort of special. It's a function from R to S1, from real numbers to the circle, but this function is what one calls a covering map. This is what one calls a covering map. And this is the part where I'm not going to get into it, but I'll just give you a general idea of what a covering map is. A covering map is basically saying that locally points around R. So if you're an ant living on R, and if you like map yourself to S1 by this map P, then locally the R around you looks kind of same as in the image. Like if you look around yourself in R, it's same as looking around yourself in S, in the circle S1. So local neighborhoods are the same. So because locally around yourself will just see an open interval. Of course, R globally is different from S1 because globally R is that you keep going forever, while S1 is globally different because in S1, if you keep going, you'll eventually come back to your starting point. So S1 and R are globally different, but locally they look the same. So that's kind of what it means. So this function P is kind of a covering map. That's all that means. But okay, that's a very non-technical, sketchy definition, but we'll work with that. The other thing to note is that, so it's some map, which we call covering map. But the other thing to note is that this guy S2, it's what we call connected. Connected, I can explain. Connected means that any 2 points on S2, I can walk from there to the other. So if you give me any 2 points on the surface of Earth, there is a way to walk from there to there. I mean, on the Earth, you might have to swim, but there is like a way. On S2, there is a way to get from any point to any other point by just walking. Okay, so that's what connected means. That's easy. But more importantly, and this is really the heart of it, it's what one calls simply connected. It's not just connected, but it's what's called simply connected. So simply connected, again, I'm just going to give you a vague definition, not the exact definition, but simply connected means that if I take any loop inside S2, so draw a closed curve inside S2, any closed curve you want. So if you draw a closed curve inside S2, I can gradually shrink that closed curve to a point without leaving S2. Okay, so on the surface of S2 itself, I can shrink any closed curve down to a single point. Okay, so that's what it means to be simply connected. So S2, for instance, is simply connected, while S1 is not. The circle is not simply connected because on the circle, I can draw a closed curve which just goes around the circle. Just here is a circle, I can draw a closed curve which goes around the circle, and there is no way to shrink that to a point, without leaving the circle. But on S2, I can do that. For instance, in S2, if you draw a closed curve, which is the equator, like think of the S2, it's the surface of the Earth. If I draw the equator, which is a closed curve, I can shrink it to a point by I just like basically push this equator to the North Pole, like gradually just shrink it and move towards the North Pole. And then I've shrunk it to a point. And in S2, it turns out that everything can be shrunk to a point. So it's simply connected. This one is not. S1 is not. Okay. So if this is the setting, if like this guy is a covering map, this guy is simply connected and connected, then there is a theorem. Again, we are not going to prove this. There is a theorem which says that I can factor H through P, or in other words, I can construct a map, continuous map. Let's call it H tilde. I can construct this map H tilde. So there exists H tilde. So I can construct a map H tilde from S2 to R, which kind of lifts H, or in other words, maybe I'll just like push it down, or in other words, I can lift this so that if I do H tilde and then I do the projection P, then I do the covering map P, that's the original map H. Okay, so I have this map H, I have this map P, and then this basically says that there is a continuous map H tilde from S2 to R, so that it factors like that. That first I do H tilde and then I do P, it's same as just the map H. Okay, so this is kind of the heart of the theorem, and this is the theorem. This is the part that you won't learn until until grad school maybe. But I mean, unless you do topology, this is kind of the theorem. But let's assume that. So let's keep going. Okay, so I don't want to get like too bogged down because I wanted to also tell you like some other applications of Borsuk-Ulam theorem. But this is a theorem. And then how does that help us? So we have a map H from S2 to S1. And then we get this map H tilde from S2 to R, which kind of lifts this. Okay, so what? Well, there is a little bit trick still left. So then what I can do is like I basically keep using the same picture. Well, remember I keep talking about the equator. So the equator is it sits inside S1, S2, right? So here is S1. S1 is the equator, and that sits inside S2. So here is S1 sitting inside S2, right? So the S2 contains the equator. And I still have this function H tilde on that, right? I mean, like this function, this blue function kind of exists on S1 as well. So I can still define, like I have this function H tilde defined on the whole sphere. So I also have this defined on the equator. And then what do? Well, then I use this one-dimensional version of Borsuk-Ulam theorem that we just learned. Okay, so we just use that one-dimensional version of Borsuk-Ulam theorem. And what does that tell us? That tells us that some two antipodal points on this equator, on this S1, for some two antipodal points on this equator, H tilde must take the same value. Okay, so this is what Borsuk-Ulam theorem tells us. Sorry about that. So by the one-dimensional Borsuk-Ulam theorem that we just did, so there exists some antipodal points on that S1 so that H tilde of X is H tilde of minus X. So some pair of antipodal points on that as equatorial S1 must map to the same point in R. Well, then if I project it, so then if I apply this projection map, it still must be the same. So if I project that, it still is the same. If I apply the map P, it still is the same. But applying first H tilde and then the map P is same as just applying the map H. So this equation just means that so P is the first H tilde, then P is just same as the map H. So this is just saying that H of X is H tilde of X. So sorry, H tilde of minus X. I want to put a minus X everywhere. I'll try minus X. Okay, good. So H tilde of X is H tilde, sorry, H. I'm like, is H of minus X. Great. Good, but I also already knew, so this is actually, but I already knew that H was odd. I knew H was odd. So I also know that H of X is actually, H of minus X is actually minus H of X because it's an odd function. I already know that this guy is actually minus H of X because H is odd. This is because H is odd. So if I negate the input, I negate the output. So I get that H of X must be minus H of X. But that's impossible because H is a point in the circle. On the circle, no point is its negative. Like H is a point, H of X is a point in the circle. So let me write it. So H of X is a point on the circle. And on the circle, if you take any point and you take its negative, that's not the same point. That's some other point. Okay, so this part is impossible. And that's your contradiction. Okay. Okay, good. Any questions? So that's actually a very brief sketch of this Borsuk-Ulam theorem. So it's not obvious, but it proves that if I have a two-variable function on the surface of a sphere, then there are 2 points which must have the same value. It's very stunning. And it's not obvious. It's not easy. The one variable case is nice. That already is a fun thing. And that hopefully is accessible to everybody. The two variable case is not obvious. And that it actually use this thing called topology. OK, we use the fact that somehow S2 is simply connected. Every loop can be shrunk to a point. That was very important, that every loop could be shrunk to a point. So really the heart of the proof, let me show you once again. The heart of the proof is right here. That I could construct this map H tilde. I could construct this map H tilde, and that really used something about the topology of S2. The fact that S2 had every loop could be shrunk to a point. Okay. No questions? Fine. Then we'll do some applications of Borsuk-Ulam theorem. So, I mean, one application is already this thing that I've been keeping on telling you, because it's already a stunning statement that some 2 points on the surface of Earth, some 2 antipodal points on the surface of Earth have the same temperature and pressure, because temperature and pressure are continuous functions. But let's say more sort of stunning applications. So another one of my favorites is this thing called the let's say well, there are many, but which one should I do first? So there is this thing which says that, well, let's the famous ones. Let's say do the one called Ham Sandwich Theorem. This is very interesting. So it's called the Ham Sandwich Theorem. Okay. I mean, I guess in India you don't get that much ham sandwich, but you can think of it as chicken sandwich theorem. Okay, so so if you want, you can call it chicken sandwich theorem. But Actually, I remember when I was in ISI 2002, right? So there was actually, it was even hard to find chicken sandwich near ISI. But then they opened a cafe coffee day near RV College. So if anybody knows like ISI, somebody like, on the next bus stop, there is like an RV College and there is a cafe coffee day. They had chicken sandwiches. So we would walk there to get that. But anyways, so you can think of that. But okay, so what is ham sandwich theorem? It basically says that, let's say, so you have one sort of sandwich. It has bread, it has chicken or ham, whatever you want, and cheese. Okay, so it has three ingredients. So bread, chicken, and cheese, and then there is a way to just slice it in one single slice, like by one single plane. There is some plane in which you can slice the thing so that both sides have the same amount of bread, the same amount of chicken, and the same amount of cheese. Okay, you can like slice in one single slice so that you have like there are two people and they will get equal amounts of both bread, chicken, and cheese. Okay, so that's called the ham sandwich theorem. It's again a sort of very stunning theorem, and it follows from Borsuk-Ulam theorem. Let's see how it like follows. It's an application of Borsuk-Ulam theorem. Okay, so sorry, let's see. So I'm not going to write it, but so the way to think about this is that so you can think of like so here is a sandwich in space. So there is this chicken part and there is the bread part and there is the cheese part, right? So I can think of them as like three subsets of R3, So there is like the bread. So I have a subset bread. I have a subset chicken. Oh, chicken, not ham. Let's just say ham, like because it's a different letter. So I have the subset bread, I have the subset ham, and I have the subset cheese. So these are three subsets of R3. These three subsets. So we can think of, you can assume that these are like sort of, I mean, it's not an infinite subset. You don't have an infinite amount of bread or something. So it's just like finite subsets. So like bounded subsets. So we call these like bounded subsets. So we call them like compact subsets. These are three compact subsets. If you know what a topology is, then you know that what a compact subset is. Compact subset essentially means it's bounded and it's also closed. It's a closed bounded subset, okay? Like a closed interval. So these are three compact subsets of R3. Doesn't matter, some three compact subsets, the bread part, the ham part, and the cheese part. And then I'm saying that there is some plane, which cuts each of them into equal pieces, equal volumes, like which slices them, and the thing on the left and the thing on the right, they are equal volumes. Okay, there is some plane which cuts these three things into equal volumes. Okay. There exists, let me write it, there exists a plane which cuts each into two equal volumes. Okay. So how do I prove this? And how is this like related to Borsuk-Ulam theorem? Okay, so all these applications of Borsuk-Ulam theorem are all themselves very tricky also. So what I do is that first of all, I fix a direction of a plane. So first of all, what does it mean to fix a direction of a plane? That means I fix a normal direction. So a direction of a plane is same as the direction of its normal vector. Okay, so you fix a normal vector, a unit normal vector, and look at all the planes which are perpendicular to that. Okay, so fix some unit normal vector. So I'm not going to write everything out because first of all, writing is very hard on this like computer screen, and then maybe it's better if I just say things. So fix a normal direction and look at all the planes which are perpendicular to that. So here is a plane which is perpendicular to that, but you look at all the planes which are parallel to that. So as well, so you look at all the planes which are perpendicular to a fixed normal directions. Okay, so that's a one parameter family of planes because you can like keep going up and down. Okay. Now let's look at the bread subset. Okay, there's a bread subset somewhere. There is some subset called the bread subset. It doesn't really have to be connected, but there's some subset called the bread subset. And then, but it's bounded. There's only a finite amount of bread, so it's bounded. So if I move my plane sufficiently high up, the entire bread is going to lie on one side. On the other hand, if I move it sufficiently far down, the entire bread is going to lie on the other side. Okay, so if you move it sufficiently far up, for a fixed normal direction. So you fix n. I should have said this. Let me just write that. You fix n. So you're looking at a fixed normal direction and you're moving the plane up and down. So if you're sufficiently far on one side, the entire bread is on the right side. If you're sufficiently far on the other side, the entire bread is on the left side. So by intermediate value theorem, there is some point in between where that plane cuts this bread into equal pieces. Okay. So there is some intermediate plane in this direction. Let me draw it. So there is some intermediate plane which cuts this into two equal pieces. So for the bread subset, there is some direction in which it cuts the bread into two equal pieces. Well, if there is more than two directions, you just take the middle one. Okay, I mean, this is small technicality, but I'm going to skip that. Okay, so if there are two directions, or if there are multiple directions, sorry, if there are multiple planes which all cut the bread into equal pieces, you just take the middle one. So there is one plane and just take the middle one, which cuts the bread into two equal pieces. But the point is that in every direction, there is some plane. Okay, let's call this the plane, this plane, let's call it the plane in this normal direction n. Let's call it Pn. So n was a normal direction and let's call this plane to be Pn. So look, so that's a plane whose normal vector is n and which cuts the bread subset into equal pieces. Okay, any questions up to here? So but I have to also cut the ham subset and the cheese subset into equal pieces. But I have lots of planes available because I have one plane in each normal direction. In each normal direction, I have one plane which works for the bread. So the bread I've done. Okay, so now what you do is you define a two-variable function from the circle to R2. So here is your two-variable function. It's always the Borsuk-Ulam theorem. Okay, it's always the Borsuk-Ulam theorem. Where is it? Yeah. So here is a different two-variable function from S2 to R2. So points on S2, I can think of it as a unit normal vector. So these are like, just remember, these are like unit normal vectors. Unit normal vectors. So, sorry, unit vectors. Sorry, by normal, unit vectors. These are like unit vectors. Points on S2 are like unit vectors in R3. Okay, so kind of like things that we have been calling n hat. Okay, so I can think of them as n hat. And then this function is the following, that you look at this plane Pn hat, that we just defined. You look at this plane Pn hat. So it's a plane which is perpendicular to n hat. You look at this plane Pn hat, which is a plane perpendicular to n hat and which cuts the bread into two equal pieces. So you look at the plane Pn hat and you see the amount of chicken, the volume of chicken, sorry, volume of ham, that's to the left of it, or like that's to the direction in which, so like, okay, let me draw a picture again. So if I look at this plane, let's look at the plane Pn hat. So let's look at the plane Pn hat. It's some plane like that. It cuts the bread into two equal pieces. I know that, but it has one direction, which is the direction of n hat. It's one direction, which is the direction n hat, and it has the other direction, which is the direction minus n hat. So this plane cuts R3 into two pieces. One direction is the direction n hat and the other direction is the direction minus n hat. Okay, so to look at the direction, which is the n hat direction, and then what you do is you look at the amount of chicken. So sorry, ham. So f of n hat. So I'm going to define this function n hat. So f of n hat. So it has to be two real numbers. It's two real numbers, and this is the volume of ham in this direction, in the direction of n hat, volume of ham. Sorry, let me just write the full thing. Volume of ham that has been sliced, the volume of ham that is like sliced by this plane Pn hat in the direction of n hat, comma, same ditto for the volume of cheese. Okay, volume of cheese, the same definition. So the function, it's two real numbers, and the two real numbers are like the amount of ham that it cuts on one side and the amount of cheese that it cuts on one side. So it's a two variable continuous function. Remember, p n hat already cuts the bread into two equal pieces. It already cuts the bread into two equal pieces, but I just learned that, and I just defined it to be like this. Okay, and then I get that, well, the thing to notice is that by Borsuk-Ulam theorem, so then we are done by Borsuk-Ulam theorem. So by Borsuk-Ulam theorem, there is some point so that, let me finish this. So by Borsuk-Ulam theorem, I mean, there is some direction so that f of n hat is same as f of minus n hat. Okay, but how can that happen? How can f of n hat be same as f of minus n hat? Let me draw this again. So if this is n hat, if this is n hat, and if this is minus n hat, well, if here is a plane p n hat, if this is the plane p n hat, so remember, this is the plane that cuts the bread into equal volumes. Well, if this plane cuts the bread into equal volumes, that same plane, must cut the bread into equal volumes. So this is also the plane p of minus n hat, right? I mean, like, when I'm looking at planes which are perpendicular to n hat, those are also planes which are perpendicular to minus n hat. Planes perpendicular to n hat are same as planes perpendicular to minus n hat. So if p n hat cuts into two equal volumes, well, it cuts into two equal volumes. So that's also the plane for p minus n hat. Remember, that's why I said that if you have multiple planes cutting it, you just take the middle one. So p n hat is same as p minus n hat. So this plane cuts the bread into two equal volumes. But then I learned that, well, this function is equal to its value on the negative. But f of n hat, see, f of n hat is actually the amount of ham on one side and the amount of, let's give it colors, amount of ham on one side and the amount of, so maybe orange is ham and amount of cheese on the other side. So this is cheese and this is ham. So f of n hat is the amount of ham on one side and the amount of chicken on that side. But it's the same plane. It's the same plane. So f of minus n hat is the amount of ham on the other side and it's the amount of cheese on the other side. So I just learned that they're actually equal because f of n hat is same as f of minus n hat. So this plane actually cuts the bread into two equal volumes as well as the ham and the chicken. Okay, so and the cheese. So that's your theorem, right? So that's called the Ham Sandwich Theorem. I mean, it's typically called the Ham Sandwich Theorem, but the theorem is very stunning. It basically says that if somebody gives you three sort of compact subsets of R3, anywhere, actually, they don't even have to be connected. Your bread or your bread is typically not connected. It's two pieces. But it doesn't matter. If somebody gives you three subsets of R3, three pieces inside R3, they don't have to be near to each other. They don't have to be connected. They could be disconnected. They don't have to be next to each other. Doesn't matter where they are. There is some plane somewhere which actually slices all three of them into two equal volumes. Good? Questions? So that's a very stunning corollary of Borsuk-Ulam theorem.
Can this be proved more elementarily?
No, I don't think so. I mean, Borsuk-Ulam theorem is not very elementary, and
not Borsuk-Ulam theorem. I'm just talking about the Ham Sandwich theorem.
No, I don't think so.
Okay, so
I think it's sort of equivalent to Borsuk-Ulam theorem. So if you can prove Ham Sandwich theorem, you can most probably also prove Borsuk-Ulam theorem by the same method.
Sir, I have a question.
Yeah.
That suppose you take the three variables separately. One is the bread, then the ham and the cheese. So for the bread part to be divided equally, you find one plane. But how can you assure that that plane will always divide the ham and the cheese equally? That may not divide. They may have some other plane.
No, I'm not doing this that way, right? So you see, the proof is not very sort of straightforward. I am not taking separate planes which separate the ham and the cheese equally. I am only it's sort of the bread and the ham and the cheese are actually treated separately. They're actually treated in not symmetrically. So I am, first of all, in every direction, I'm fixing a direction. Let's go do this proof again. Okay, I'm fixing a direction and I'm looking for a plane perpendicular to that direction, which cuts the bread equally. Okay, I'm not doing the same thing for the ham and the cheese. I'm just doing it for the bread. Okay, but now in every direction, I have found a plane. Actually, such a plane exists in every direction. So in every direction, I have found a plane which cuts the bread equally. I don't care about the ham and the cheese at all. Okay, but in every direction, I have found a plane which cuts the bread equally. Okay, and the thing is to note is that the plane in the opposite direction is actually the same plane. So if you are looking for the plane in the perpendicular to n hat, it's actually the same plane if you think of it perpendicular to minus n hat. So if you change the direction, it actually is the same plane because it still cuts the bread into two equal pieces. So in every direction, I have found a plane which cuts the bread into two equal pieces. Okay, so that part is easy. But now I use the Borsuk-Ulam theorem. I define this function where, like, look at this function. The function is that it's a two variable function. It's a two variable function. So for every normal direction, for every unit vector, I look at this plane which cuts the bread equally. And then I just count what is the volume of ham on one side of that. And what is the volume of cheese on one side of that. Okay, so for the cheese and the ham, I'm actually using the Borsuk-Ulam theorem. So for every direction, you look at that plane and look at the amount of ham and the amount of cheese on one side. Okay. And then, sort of amazingly, by Borsuk-Ulam theorem, it says that there is some normal direction. There is some normal direction where the value of f will be same as the value of f on minus n. Like f of n will be f of minus n. There will be some normal direction where this will hold. But that just means that for that specific normal direction, if I look at this plane P, the amount of ham on this side and will be same as the amount of ham on the other side. Amount of cheese on this side will be same as the amount of cheese on the other side.
How do we get to cheese? I mean, we were doing it for the bread, like that is given. Then we move to ham. Then
how do you move ham? So see, do you see this statement?
The volume of ham, yeah. We are finding out the volume of ham sliced on either side, and by Borsuk-Ulam we can find like
no. Sorry, you're not reading. Sorry, let me just show it again. F is a function from S2 to R2. It's a two variable function. Remember, it's like pressure and temperature. So you're looking at pressure and temperature on the planet on the surface of Earth.
Is it like means what are the variables, ham and cheese?
Let me do it again. So look, let me square this. Let me put this in a rectangle. So on the surface of Earth, you have two variables. Okay, your output is two variables. It's two real numbers. Okay, one real, like for every normal direction, the output is by two real numbers. Okay, so do you see the two real numbers? The first real number is the volume of ham in one direction, in one side, to the left side of the plane.
Volume of ham, yes.
Yeah. Do you see the second variable is the volume of cheese on that same direction, on the same side. So it's two variables. There's like output number one, output number two.
Now we define that map, and therefore we can say by Borsuk-Ulam that there is
some plane where both of the values are equal, right?
Both of the values are equal. But minus n also gives the same plane, right? Because minus n and n are.
That's right. That's right. Minus n gives the same plane. That's right. So this is this picture. So there is like some direction where they're equal, but that plane is the plane for both n and minus n. So that's why that, yeah. But
that plane is therefore unique.
Not necessarily. I never said that in Borsuk-Ulam there is a unique such plane.
Oh, there is not unique. There is existence only. Yes.
Yeah, that's right. That's right. Yeah. So like I said, Borsuk-Ulam is not obvious. Borsuk-Ulam is actually a hard theorem. I mean, it uses some technique that you only learn in grad school, like during PhD. So, and only if you're doing topology. So it's not obvious. And I think the corollaries of Borsuk-Ulam are also not obvious. Like this is like not something you'll most probably be able to solve in like even in like undergraduate college level. Okay. So because this theorem is a hard theorem. Okay. It just happens that it's a hard theorem, but it has this nice statements, like nice corollaries. They all have names. Like, you know, the surface of Earth has like 2 points, 2 antipodal points with same temperature and pressure. But that's actually a deep topological theorem. It's not easy. It sounds easy. It's not easy. Like this statement sounds easy, but it's not easy. It's like Yeah, just like it's just like sounds like a nice statement, but not an easy statement. Okay, so
Sir, I have a question.
yeah,
Sir, where we defined that p, the function p, we had
yeah,
said stated that e equal to that p is equal to 2 power e pi e power 2 pi I t. So we can just write that e to the power I pi to be -1. So what's the difference then?
I
Why
pi.
are we writing in that fashion?
Sorry, what do you mean? E to the power what?
E to the power I pi is -1.
Yeah.
Uh,
So
then we could have written that p to the pt is equal to I 1 -1 to the power 2t. So
no,
that
that
we
doesn't work like that. No, that doesn't work like that. It only works for like integer t. That's right. So this is like this is the only way you can write this. Yeah, it's like it doesn't work like that. So yeah. Um, because t could be like t, if t is an integer, you can do that. But if t is not an integer, if t is like say half, okay, then how do you define like -1 to the half? Let's say t is 1/4. Okay, let's say t is 1/4. Let's do that. Let's say t is 1/4. Then you are saying that e to the I pi is -1. Very good. But then t is 1/4, right? So then I still have to like do -1 to the power 2, right? So that's -1 to the power half. So that means that's the square root of -1, right?
okay, understood.
So how do you define -1 to the half? So actually you define it by this formula. You're coming back to this, yeah. So it doesn't make sense. Yeah, you don't do like this is like the simplest
But its
formula.
modulus is 1.
In modulus is always 1. That's right. So it's always a point in the unit circle on the circle of radius 1. That's like some complex analysis, some simple complex numbers that you may or may not know. Okay, depending on which class you're in. But yeah, so it's a complex number. It's always a unit complex number. So that's why it's a point on the circle. Yeah, it's a very important map, this map, you know. But yeah, so if you do math, you'll see this map over and over again. Okay, more questions? Okay, if not, I'll just like let's see if I have time to do one more of these applications, but maybe I don't have time to do one more of these applications, but I'll just state this. So there is this thing that if I look at subsets on S2, which so here is the surface S2 again. Okay, and let's say S2 is the union of 3 closed subsets. I mean, it's a union of 3 closed it's a union of 3 closed subsets. So these are closed subsets, not necessarily disjoint, but these are closed subsets, whatever that means. These are closed subsets. Then one of them must contain a pair of antipodal points. I'll just write. Then one of them, at least one of them, must contain antipodes. Okay, so I'll leave it to think about it. This one looks very much like Borsuk-Ulam, right? I mean, this one, you know, maybe it seems like a Borsuk-Ulam theorem to you. But anyways, so but why is that? So it's an interesting theorem. That means, like, for instance, like it actually has a corollary. Like, so remember, like, you know, here is like Earth again. Let me draw Earth. Here is Earth. And you know, so there are these like GPS satellites or whatnot, and that they like cover Earth, right? So here is like a GPS satellite, but or satellites which like, but each satellite sort of only sees at most half of the Earth, right? I mean, it can only communicate with at most half. I mean, not even the whole half thing. I mean, something less than a half. So the amount of region covered by a single satellite is always on one side of the planet, doesn't matter where it is. It's always less than actually one side of the planet. And so the region covered by a single satellite can never contain a pair of antipodes. So this never contains a pair of antipodes. This does not contain antipodes. That's the way it is. It does not contain antipodes. So the region that's seen by a single satellite does not contain antipodes. So this means that if I need to like see every point on Earth, if I want to cover every point on Earth, I need at least 4 satellites because 3 of them won't do it. This theorem says that 3 of them won't do it because if I try to cover the entire surface of Earth with 3 subsets, with 3 regions, doesn't matter how I put them or how complicated the regions are. If I try to cover Earth with 3 regions, one of them must contain a pair of antipodes. So the regions covered by the satellites don't contain a pair of antipodes. So this actually has a nice corollary that if I want to cover need at least, it's again, maybe not obvious, need at least 4 satellites to cover Earth, to cover the whole Earth, okay? I mean, that's not an issue. We have 10,000 satellites covering Earth. So, but the theorem is that, you need to cover it, you need at least 4. And that's because of this thing that if I want to cover circle like the sphere with closed subsets, 3 of them, then at least one of them must contain a pair of antipodes. Okay, so let's try to see why this is, again, this is application of Borsuk-Ulam theorem, but just like Borsuk-Ulam theorem itself, the applications are also not straightforward. I mean, the applications are themselves all tricky also. So this one sounds very Borsuk-Ulamy. It's not obvious, again, it is not obvious, but how would I do this? Like, why is this just an idea? Okay, maybe I'll just leave a little bit of this as an exercise, but why would this, how do you try to get this? Try to put this in a Borsuk-Ulam form, right? Do you see this idea or? So I want to construct, remember, always our idea is that we want to use Borsuk-Ulam theorem. So we always want to construct a function from S2 to R2. Okay, I want to always construct a function from S2 to R2. And then if I have any continuous function from S2 to R2, I know that some 2 antipodal points, the value will be the same. So, okay, maybe I am just slightly running out of time. So you can think about this. So I'll give you a hint. Okay, I'll not tell you all the answers because the answer is also in Wikipedia or something. So, I'll just leave a little bit for you to research yourself if you're interested, because you look for applications of Borsuk-Ulam theorem. I don't want to tell you all the answers. And also it's good to think about it and just for practice, because if you just know the tricks, if I just tell you a bunch of tricks, it's not as fun. Okay, so it is slightly tricky, but I'll give you a idea, hint that, I mean, you can try to look for distances to these subsets. So if I have a point X, so I'm not going to tell you the solution. The hint is that if I have a point X on S2, you can try looking at distance of X to this subset Ci. So this is distance. So distance on the surface of Earth, how much do you have to travel? So X is a point on Earth. You are standing in some point on Earth, and there is some subset Ci. There is some subset Ci. You can ask that, how much do I have to walk from X to get to Ci? Okay, what is the amount of distance I have to walk? So you can try to think of this type of functions. Okay, so using these distance functions, but you want to use these distance functions and then come up with some function like this. And then so that once you apply Borsuk-Ulam theorem, you get whatever result you want. Okay, so let me stop there, and then if you have questions, you can ask me.
Sir, you told that a satellite cannot cover totally half part, so it can cover 1/3. So sir, if we use 3 satellites, then 1/3, 1/3, and 1/3 will make 1. So the entire satellite won't, entire Earth won't it be covered?
No, that's right, because by Borsuk-Ulam theorem. There is no way to put like 3 of these pieces together so that it covers the whole Earth. Yeah, it's pretty nice, right? I mean, so you can definitely cover almost up to almost half, right? So definitely you can do more than 1/3. But even then, 3 of them is not enough. That's right. So actually, thanks for bringing that to attention. Yeah. So there is no way to stack 3 of these pieces together. 3 of these pieces, which are like almost a half circle, almost a semicircle. Like you can make it as close to a semicircle as you want. Like essentially, so essentially three things which are as close to a semicircle, hemisphere as you want in whatever direction. You take 3 things which are as close to a hemisphere as you want in 3 direction, and you still cannot cover Earth. You need 4 of them.
I have
I
like
think it
an
is
idea for
because
why this. If you have 3 satellites, they define a plane. They are points which define a plane. So if we assume that plane to be the equator, then you will never be able to cover the North Pole and the South Pole.
That's right. Yeah. So this is actually not very. This one can be done directly, kind of. That's right. So this is because this is just about circles on Earth, right? So you're right. Yeah, that I think works. Yeah. So this is actually just about disks on Earth. So this actually is an easier thing. But this statement is harder because here this is true for any sort of closed subsets, not just like things like disks, not just things like hemispheres. That's right. So you're right. I think that just works. But that's also very interesting. It's a nice thing to notice. But this is actually a more general statement that it works for any sort of like closed subsets that 3 of them must be the same. That's right.
Sir, what is a closed subset?
What is a closed subset?
What is a closed subset?
Yeah, this is some topology thing. Sorry. So it's like a closed interval. So, closed subset is like, I'll just tell you inside. So this is actually a topology statement. So I'm not saying, so this is actually a topological statement. So something like an interval is a closed interval. So closed is something which contains all its boundary. So something like, the set, this set that, sorry, I'll try to write it. So 0, I'll stop here, by the way. I'm just taking questions. So some set like that, that's a closed interval because it's all the points which are between 0 and 1. But in particular, it contains its boundary points. So the 0 and 1 are the boundary points. So 0 and 1 are the boundary points. So if it contains all its boundary points, then it's called closed. But something like this is actually not a closed subset. Something like 0, 1, it's all the points which are between 0 but strictly less than 1. It is not a closed subset because it doesn't contain this boundary point. So 1 is kind of like a boundary, but it doesn't contain that boundary point. So closed is something that contains all its boundary points, except now that I haven't defined you what a boundary point is. But if you do topology, you'll see all these definitions. But these are examples. This is an example of a closed subset, and this is an example of something which is not a closed subset. Okay. So this is only true for closed subsets. But yeah,
I was just thinking the problem in a different way. That if we cut the Earth is a sphere. So if we cut the Earth in just 4 halves, then we will get the surface of the Earth also gets cut in 4 equal parts. So now if we take any of the parts, then no such parts contain an antipodal point. And if we just eliminate that and just adjust it to make it 3 parts, so that the whole covered the sphere, the surface of the sphere, then that must contain an antipodal point.
See, that's not a proof, right? Because you're just taking some very specific examples. Here I'm saying for any examples, it must contain any 3 of them. Yeah, it's not just like for any specific examples. So you cannot just like take, yeah, so you cannot like, I'm saying here, this is true for any closed subset, C1, C2, C3, not just like things which are like hemispheres. For any sort of closed sets, this is true.
Sir, I think in one way we can do it, like if we take at first 2 satellites, so none of them will contain any antipodal, means each of them will not contain 2 antipodal points, and so there will be some region left, and that region means the region which is not covered by any of the satellites, that will contain at least one set of antipodal points, and which cannot be covered by any one more satellite. Therefore, 2 more satellites are needed at least. Means more 2 are needed, so at least 4 are needed.
Yeah, I agree. For satellites, is easier. For satellites, it's easier to do this, but this is a more general statement. So satellite, I just like gave it as an example, but this one is harder. So the satellite part, I'll just write this. So the satellite is so just the statement for satellite. This is easier. I agree. So the satellite, because it's you're only dealing with like some very simple types of steps, so simple types of subsets, which are like hemispheres, which are almost hemispheres. This is harder because this one really does need Borsuk-Ulam theorem. I don't think there is any way to do this without Borsuk-Ulam theorem. This one is harder because here you're taking any sort of closed subsets. Okay, this one is harder. That when you're just doing this with like, yeah, so I agree. Like somebody said that you can just, if you have 3 satellites, you can just like look at the plane spanned by those, and that kind of works already. Yeah, that proof kind of works. So, but this one is harder. That for any arbitrary subsets, at least one of them must contain antipodal points. Okay, so any other questions? Okay, so maybe I'll stop sharing. Yeah, I'll try to do this as a homework. I mean, the solution is on the internet. I mean, like, but I don't have time to explain. But yeah, and there are many more applications of Borsuk-Ulam theorem. It's a very hard theorem. It's a very interesting theorem. Has very nice applications. Okay, so and all the applications can be stated in like English with like nice examples. So it's one of my favorites. Okay, I'll stop the video, and I will stop sharing. Okay.
Thank you so much, sir. That was a really fascinating and educative talk. If there are no more questions, then we may end the